Okay, hi everyone. So in this video, we're going to be going through one of the topics that we need to cover, and is a very useful topic used in not only performing calculations and making calculations easier, but also in doing proofs involving matrices. And that's the idea of block matrices. Okay, so let's see what a block matrix is. So matrices could be cut into blocks, and these blocks are just smaller matrices. And a good example of this is if we consider this 4 by 6 matrix. So there are 4 rows, right? So 4 rows and 6 columns. And for this particular matrix, you could cut a matrix into blocks of any size. So that is up to you. But notice if we cut it into these 2 by 2 blocks, then each of these blocks is the 2 by 2 identity matrix. So in other words, I could rewrite A as simply this form. So now we understand that if we see a matrix A and the entries, you don't see numbers, but instead you see a matrix, then you know right away that this is a block matrix. Okay, so you should know that this is not just a single entity. This here represents a matrix inside of it. Um, and it turns out if we have a matrix, uh, we could perform typical matrix operation if we break it into blocks of the correct sizes. What do I mean by that? So suppose we have another matrix B that is of the same size, 4 by 6. Then if we break this same matrix B, well, same size matrix B, if we now break this matrix B in the same way into little 2 by 2 blocks, okay, then we could add the matrix A plus B a block at a time. Now, of course, you all already know how to add two matrices, A plus B. You just add them component-wise or entry-wise. First entry with first entry, with second entry, and so on. So this is just saying you can add them one block at a time. And we've actually already seen this idea of block matrices. For example, when we were solving systems of the form AX equal B, and this A was a matrix, this X was a column of numbers, so what we call a column vector, and B was also a column vector. And one way to solve this system is to use A and B and form what is called the augmented matrix. And that is you take the matrix A, here's A, and you take the column vector B, and you form a new matrix where you have A, so this is A, and then you put the column vector B next to it. So this is an example of a block matrix. Okay, and we will write it as A, B, right? So this is an example of a block matrix. And if A happened to be, let's say, an m by n matrix, then of course here will be a n by 1, and B should be a m by 1. Then this block matrix, the augmented matrix, is a block matrix consisting of blocks of sizes m by n, and of course, m by 1. And uh, maybe you notice if you have to perform um, matrix multiplication of the augmented matrix. So let's say we are now, if I have to, let me see, if I have to multiply this augmented matrix, A, B, by some other matrix, so the augmented matrix totally, what is the size of this? So it's same m rows, but the number of columns is n plus 1, right? It's n plus 1 columns. because you have the original n columns from A and you have an additional column corresponding to B. So if I were to multiply it by, let's say, matrix E, and this matrix, in order, if here's m by n plus 1, then here should be, let's say, just say k by m, then this matrix multiplication, you can actually perform it a block at a time. So what you could do is, instead of treating it as two matrices, E and the augmented matrix, you can actually take the matrix E and multiply it by the matrix A, and that will give you a matrix block. And then you could take the matrix E and multiply it by the column of numbers B, and that will give you another block. So the moral of the story is that so long as you break up your matrix into blocks of a particular size where it is compatible with the other matrix operations such as addition or matrix multiplication, then you can actually do those operations block by block instead of you're used to doing it entry by entry, first row, first column, second row, second column, and so on, right? And instead of doing that, you could do it block by block. So this block, and an important thing when you're doing this block matrix stuff is to keep track of the size of each blocks. So the size of this block, EA, right? So this is very easy to work out because we know the size of E is a K by M, and A was a M by N, right? The original A was a M by N. So the resultant matrix EA, right? So here it's the same. So the resultant matrix is a K by N. K by N. Okay, so this is a K by N block. And this block, EB. Well, E by B, so M and M is the same, right, with B. And K by 1. So EB will be a K by 1 block. Okay. All right, so let's continue. So let's look at block multiplication and elimination. So if the cut between the columns of A matches the cuts between the rows of B, then block multiplication of the matrix AB is unlocked. So what this is saying is, well, again, how do we do matrix? Let me go to the next page. How do we do matrix multiplication? So we do matrix multiplication row by column, right? We do matrix multiplication if here's M and here's N. Then we do matrix multiplication row by column. Okay, so that's supposed to be a column, right? So we do it row, these elements in this row, multiplied by these elements in these columns. So what they're saying over here is that if you cut the columns of A exactly to match the rows of B, because in order to do matrix multiplication, in order to do matrix multiplication, let's say this is P by Q, and let's say this is R by S. In order for this to work, these two numbers here must be the same. So here should actually be a Q. So that's what they're saying. You need to cut it in such a way that when you do the block by block, the inner numbers must be the same, and the size of the block will be the outermost numbers. So if you do it in this way, for example, let's say you have a matrix A and you cut it in these blocks. So made up of, in this case, it's made up of 4 blocks. And let's say you have a matrix B and you cut it into, again, a certain number of blocks, then the corresponding answer, you could take this first block by this first block. So remember, it's row by column. So it's first row by first column. So what they wrote here is just for the first two columns of B. So it will be A11 by B11, and this here represents a matrix multiplication. And then it will be A12 by B12, and this here represents a matrix multiplication. And again, the A's, the A11, A12, A21, A22, these are matrices, right? Because this guy is a block matrix. And these matrices, A11, has to be compatible with B11 such that this matrix multiplication makes sense, right? So the inner dimensions need to be the same number. Okay, so you could actually do the matrix multiplication block at a time instead of entry at a time, right? Um, so this equation is the same if the blocks were numbers. So now we could view regular matrix multiplication as a special type of block multiplication. So regular matrix multiplication, we multiply numbers by numbers, right? So the entries are not matrices, they are numbers. But we could view a single number as simply a one by one block. Okay. So when the matrices split into blocks, it's often simpler to see how they act. And so, for example, the block matrix of I's above over here, it's much clearer than the original 4 by 6 matrix. And something that is also very handy is in when you want to calculate inverses. So using inverses, a block matrix E can do the elimination of a whole block of column E. So what do they mean by that? So let's say we have this matrix multiplication. So I0 minus the A inverse I. And so let me just write that off. Okay, we'll do that here. Right, so let's do this multiplication. So we have a block matrix, and the blocks is an identity block, a zero matrix block, so a matrix with all zeros, another block with a matrix minus C being multiplied by the inverse of some matrix A, and another identity block. Okay, so again, it's important to realize that these entities are entire blocks of matrices, right? And let's just say the sizes, so the identity, of course, is a square matrix, right? Let's just say the sizes are such that matrix multiplication makes sense, right? And we are multiplying it by another block matrix, and it has blocks that I'm calling A, B, and the same C from here, and D. Okay, so these are block matrices. They are matrices, and the entries are no longer numbers, they are blocks. But let's just say that these two matrices, the first one and the second one, are broken up in such a way that matrix multiplication makes sense, in such a way that the sizes of these blocks correspond such that we are able to do matrix multiplication. Okay, and again, we also have to go back to what is the requirement to do matrix multiplication? Let me write it clear. Right? So the requirement to do matrix multiplication is that what do I call it? P, Q, Q, R. R. The requirement to do matrix multiplication is that these two numbers must be the same. So in this case, this M and N represents two blocks inside that bigger block matrix structure. And in order to do the multiplication of the M block by the N block, the size of the M block and the size of the N block must be such that these inner dimensions are the same. And the output matrix will be a matrix of the outer block. Let me put in a different color. This matrix will be a P by R matrix. Okay, but let's just say for this particular example that these matrices are defined such that those blocks are able to do multiplication. Okay, so let's do the multiplication. Then the multiplication is just normal matrix multiplication. So first row by first column. So if I multiply the identity by A, right? So let's write out everything first. So this is IA, and then 0 by C plus 0 by C. So that is the first entry in this block structure. Okay. The second entry, so let's go first row, second column. So it's I by B, right? And then 0 by D. Now, it's important again to realize that once more, these are not numbers, these are matrices. So do not switch the order around, okay? Because if you switch the order around, maybe the matrices commute, right? Maybe it is other matrices, you could switch the order around and you could get the same thing. For example, if you're dealing with the identity matrix. But it could be that the size of the block B is such that IB makes sense, but BI may not make sense. What do I mean by that? Say I, let's just say I is the 3 by 3 identity matrix, right? So you all know what that is. 1, 1, 1, zeros and zeros. And let's just say B is a 3 by 5 matrix. Okay, then IB makes sense because I is 3 by 3, B is 3 by 5. The two inner numbers are the same, right? So this matrix is a 3 by 5 matrix. But when you're doing the block matrix multiplication, you can't switch it around because if you switch it around and you put BI, does this make sense? B is 3 by 5. I is 3 by 3. The inner numbers are not the same. So this doesn't make sense. So we cannot multiply, right? So don't switch the order around when you're doing block matrices, even though it's the identity, because the matrix that the identity matrix is multiplying might be not square. Okay, so keep the ordering the same. Okay, so let's continue. Then let's fill out this entry. So that is the second row by first column. So that is minus C A inverse A plus I times C. And the last one is second row by second column. So that is minus C A inverse B plus I times D. And now we could simplify, right? So I by A is A. The zero matrix by any matrix is zero. I by B is B. So here's A, here's B. Down here, so we know that these two matrices will cancel, right? And I times C is just C. So we get minus C plus C. So that is just a zero matrix. And for the last one, nothing there really simplifies. It's minus C A inverse B plus D. Okay, so this is your block matrix structure, right? So it's the same thing up here. Of course, you could write D first if you want, because if you're adding and subtracting matrices, if you're adding like a matrix, of course, you could switch the order is if you're multiplying, right? So you see they have minus C A inverse B, minus C A inverse B. So you keep that order the same. Okay, so that's an example of how to do these block matrix multiplication. Now we're going to look at two different ways we could basically break up a matrix um, to allow us to do um, these sort of multiplication. And these are what are called row and column partitions. Okay. So before we begin, what this first part here is saying is just a word on the notation. So far, let's say, for example, R cube, right? So I think we could agree that the elements of R cubed, let's just say, look like this: x1, x2, x3. They have three tuples, right? And we write them sort of like a row going across. Um, and the elements of our 3 by 1. Okay, this is also the matrix with real entries 3 by 1, right? So that's another way to write it. So this is 3 rows, 1 column. So we can write that as x1, x2, x3. Okay, so we studied these vector spaces already, right? So you can write it either like this or either like this. We studied these two vector spaces already. Um, so we know obviously that these two spaces are different, and x1, x2, x3 written as a row, and x1, x2, x3 written as a column, a single column. These two vectors are not equal to each other, right? Because they are from different spaces. But I think we could all agree that it's pretty much the same vector. All you're doing is instead of writing as a row, you just write as a column, right? And in fact, we know the technical word for it is that these two spaces are isomorphic vector spaces. So now we're going to use that isomorphism, and we're going to say that we're going to identify these two objects together. And what I mean by that is now, anytime, well, in this section, or when we're dealing with matrices, whenever we write a vector x belonging to Fn, so some n tuple with a field, it will be understood that it is a column. Okay. Of course, what I just explained is that there's no main difference between if you write it as a row or if you write it as a column because the vector space structure is isomorphic. The reason why we choose to write it as a column is so that it makes the matrix operations that we're going to perform on it easier. Okay, so anytime you see a vector x belonging to Fn, yes, technically it is a row. So you write it as a n tuple as a row, but we'll just say, let's just agree to write it as a column. So if we want to write the technically correct version of what this vector is, that is, if I want to write it, say, as a row, then that is actually X transpose. Okay, and any vector X transpose will be represented as a row. So all you need to remember for the rest of this section is that if you see a column vector belonging to Fn, then it is a column. And if you see that vector transpose, it's a row. Okay, so that brings us to our first result. Let B1, B2 up to Bn be columns, so n columns of some matrix B. Right, and we see over here, this matrix is a R by N matrix with entries in the field F. Then the representation B equal, and then we have this as a representation, is partitioned according to its columns. So what are they saying there? So let me write the matrix B. Okay, so B is a R by N matrix. So I'll switch the square brackets just to make my life easier. So R rows, N columns. So N columns, R rows. Right? And the entries are from from some field, either real or complex, right? Either real or complex. Now these B's, right? These are vectors, and I just set up here. When we see a vector, it will be understood that it is a column. Okay, so B1 is this first column, right? So this is B1. B2 is this second column. So you see, we are writing the matrix B as a block matrix, but each of the blocks are columns, right? The blocks could be columns. And here is the um, BN, nth block, right? And if I want the size of one of these B's, right? So of course, BI, this is so as a column, it's how much rows. Well, it's R rows and how much column. Well, it's a column, so it's just one column. So these are R by one, or we could simply say it belongs to FR if you want to. Okay, so we write B in this form. So now when you see a matrix written in terms of B1, B2, and so on, it's understood that these entries here represent the columns. Okay, so the individual columns. So this is what we call partition according to its columns. And what we could do with that is if we partition a matrix according to its column, then this gives us a convenient way to do multiplication of this matrix by another column. Okay, so say we have column X, right? So now we agree that the vectors are written as columns. That's why I need to put a transpose here if I want to write it as a row. Okay, so it's a column. And I'm doing B times X, which is equal to this. And if, for example, let's just say, for example, I gave you 210 multiplied by 4 minus 1, 1, right? So this is a one row, three column. This is a three column, one row. Three rows, one column. Of course, the number in the middle must be the same for multiplication to work. And the answer is a 1 by 1. 1 by 1 is a number. Okay, so that number is, how do we get that number? Well, it's 2 by 4 plus 1 by minus 1 plus 0 by 1. Yeah, whatever that is. In other words, what is this? Where you multiply corresponding entries or components and you add them. This you should recognize as simply the dot product in Rn. Okay, so what we're doing now is we are extending this idea not just to when the entries are not just numbers, but the entries are blocks now. So each entry now is a block. And we are applying that block to the first component, the second component, to the third component. Okay. So we apply B1 to X1, B2 to X2, and so on, Bn to Xn. Okay. And of course, this here is not a number like that example that we just looked at. But we can look at the size of it because if B is a R by N and X we know is a N by 1, then of course these two numbers must be the same and the answer is a R by 1. So this is a R by 1. Okay, so R rows, one column. In other words, this thing here is a column. Okay, okay, so when you work it out. Or another way to think about it is what you see in here is the x1, x2, x3, xn. These are single numbers, right? Those are individual numbers. The B1, B2, and so on are not numbers. Those are columns. So this here is some number times the column B1 plus some number times the column B2 plus some number times the column Bn. So this should look familiar to you. This is just a linear combination of the columns. right? Linear combination means you multiply each column by a number and you add them together. So this is a linear combination of the columns. So, so this is one way of viewing um, what happens when you multiply a matrix by a column. When you multiply a matrix by a column, what you're actually doing is you are taking linear combinations of that column, of those columns. Um, an example. Okay, let me give you an example. So say we have some matrix B. I'm just going to write random numbers. Mm, mm. Right, so let's say this is your matrix. So it is 4 rows, 3 columns, right? And this one here, this is your B1, this is your B2, this is your B3. And let's say I want to know what is this. So if I'm multiplying by a column, it needs to be a 3 by 1, right? This number and this number needs to add up. And let's say I'm doing 2, 1, minus 3, right? Then what this answer is I'm taking 2 amounts of the first column plus 1 amount of the second column. So this of course is B1, this is B2, 9, 11, 3, 2, plus, well, it'll be minus 3. And so minus 3 amounts of the last column. So here it'll be 3, 1, 1, minus 4, 7. Okay, so when you do matrix multiplication of a matrix by column of numbers, what you're actually doing is taking a linear combination of those columns. And the proof of it is given here. Okay, so let's quickly go through the proof. So to prove that this is true, all we must do is we must just verify that the corresponding entries of the left-hand side and the right-hand side are the same. So I'm going to let the entries of my matrix be B, Bij. So the vectors comprise, so the vectors that comprise the columns are, right? So this here represents the jth column, right? So remember for matrix entries, if it's Bij, the I represents the row number and the J is the column number. So if I want all with column J, right? If I want all with column J, then notice they all have J as their second entry because that's the J column. Okay, so I can write the J column in this form. And now I want to work out what is B times X. Now we know if B is a R by N matrix, and if X is a N by 1, then B times X is a R by 1 vector, right? So for any I, the ith entry of Bx, right? So this is a R by 1 vector, right? So when we work out this entire right-hand side, this will give a 4 by 1, so, right? So now, so 4 by 1, right? So let's call it y1, y2, y3, y4. So now they want to know, like, for example, what is the equation for y2, right? For the second component in that vector, right? But from here, we could easily figure out how to get that. It's just, a different color. It's this one by the second one, plus this one by the second one, plus this one by the second one. In other words, it's 2, 1, minus 3. So that's this column vector X by, what was 0, 11, 1? That was the second row. Okay, so in order to get this second component, That's just the dot product of the second row with this vector x. And that is what we're trying to prove, right? So it helps in these proofs to write a matrix like what I did, like just write a small matrix and just write all the calculation and see exactly what they're asking for and work backwards and see where do these numbers come from. So now they're saying the ith entry in this vector, so bx again is a column, right? And the ith entry is over here, is just the summation of k goes from 1 to n of bik xk. This is it. This is the equation for a dot product, right? And I put here verified, right? So this equals the ith entry, and you could verify that this is just the ith entry of this vector, okay? Which is, if you look at what is the ith entry of this vector, right? So sub n b1. So when j is equal to 1, when j is equal to 2, when j is equal to n, work it out and take out the ith entries and you get that, okay? Which is the same as this, right? So that's a very handy thing for us. Now we know if we partition our matrix in columns, when we do matrix by a column vector, that is a linear combination of those columns. Okay. Now there is a next step up to this, a next generalization, and that is instead of doing like a matrix by a column X, we can now think of, instead of this column X, we could think of that as being another matrix, right? So what if we have another matrix A, which is m by n, then if we use the same column partition of B, then we could write the matrix AB, right? And again, write out and verify that these sizes are correct. That this is a m by r. If A is a m by r, then AB is a m by n, right? And B, of course, B is a r by n, right? So always verify the sizes of the matrix on each level, okay? And the entry of this matrix AB, well, it will just be the matrix A by B1. B1 is a column, right? B1 is a column like this. And if you want to get the second column of this matrix AB, it's A by B2. If you want to get the third column of this matrix AB, it's A by B3. If you want to get the nth column of this matrix AB, it's A by Bn. Now, each of this is itself a matrix multiplication. It's A by B. It's a matrix by a column. But hey, we know how to do matrix by columns, right? We just that. Right? So this representation partitions AB according to its columns, right? So the matrix AB is now partitioned in terms of its columns. This is the first column, second column, and column, each of which is a linear combination of the columns of A, right? And the coefficients are entries of the corresponding columns of B, right? So it's just like before. Okay, so we have an example. So in this example, say we have A is 2 by 2 and B is, let's write it out one time, 2 by 2 and B is 2 rows, 3 columns. So of course, these two numbers are the same. So therefore, the matrix AB will be a 2 by 3 matrix. Okay, so 2 rows, 3 columns. How do we get each of those columns? Right, so this matrix AB, we could write it as, we could break it up into its columns. So one block for the first column, second column, third column, right? My question is, what are these columns? Okay, so let's see. Well, we know from before that this column will just be, if I break up B into B1, B2, and B3, so I relabel the columns. then um, here it is. Then this first column is just A by B1. The second column is just A by B2. This third column is just A by B3. Right? And this here just verifies it. So this is the first block. This is the second block. So this is A times B, and this here is the third block. And of course, each of these inner blocks is a matrix multiplication. So you need to do row by column, 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 and you will get your answer, which of course is a 2 by 3 matrix. Okay, so it's a new way to think about how to do matrix multiplication. Of course, for us, it doesn't really change anything because we still have to do the row by column sort of matrix multiplication. But in this way, it gives us a sort of deeper or another understanding of exactly what matrix multiplication is doing. And that is, well, what we saw up here is that if we do a matrix by a column, then matrix multiplication is just taking linear combination of the columns. And if we do matrix by a matrix, then what that is doing is it's taking a each column of the resultant matrix is itself a linear combination of the second matrix. Okay, so it's just linear combinations of the columns. Now you might be thinking, well, why did we break up our matrix into columns? Why not break it up into rows? And the answer is yes, we could do that. We could go through the same process, but instead of partitioning our matrix in terms of columns that we call B1, B2 up to Bn, we could partition it according to rows. Now remember, we agree for this section that rows will be denoted by the vector transpose, and the columns will just be denoted by the vector. Okay, so if now I want to partition a matrix, so for example, a m by n matrix A into its rows, then let's see how would that look. So A is a m by n, right? So m rows, n columns, m rows, and I want to partition A. So for B, you see how we have it in columns? I want to do rows now, right? So I want to do rows. So here will be my first row, okay? But remember, I should not call this A1 because we agree if I'm writing a row of numbers, then I write that as a transpose. And if I just write a regular vector, then we agree that that is a column. So this is A1 transpose. The second row will be A2 transpose. We go all the way down. We have m rows. So this row here will be the mth row, AM transpose. Okay, so that's all what this thing here is saying. You see, A, and we break it up as this. So this is the matrix A, now partition as rows. And when we partition the matrix B as columns, we did B multiplying a vector on the left, right? And this was a column, and B was a matrix with columns, right? If you want to view partitioning a matrix as rows, then in order to get a suitable interpretation of that, we don't multiply the matrix on the left. We instead multiply the matrix. We put the matrix on the right, and we do the transpose of the vector, right? So what I mean by that? So that's summed up over here. Then we do X transpose A. So we don't do AX. right? We already covered that with BX, right? So we do A transpose X. And again, we agree that if you see a vector transpose, it is written as a row, and A is just as before. Okay, so just like before, if you were to do this multiplication, now again, remember the A1 transpose, A2 transpose, AM transpose, those are rows of numbers. Okay, so you will do A1 by A, X1 by A1 transpose, X2 by A2 transpose, XM by AM transpose, and you will get this. And now again, this is a linear combination, right? Because the X's are just numbers. This here is again a linear combination, but not of the rows of A. It's a linear combination of the, oh sorry, not, not of the columns of A. It's a linear combination of the rows of A. Okay, so if we view the matrix as being partitioned in terms of its rows, then when we perform the operation X transpose A, then that is just a linear combination of the rows. And again, we could then go back to matrix multiplication, AB. Now we already had an interpretation for AB up here, okay? And that was if we partition the matrix B as columns, then the first column is AB1, the second column is AB2, the end column is ABN. Now we are saying, so of course this matrix AB has to be equal to this matrix AB. It's the same matrix. I'm just looking at if I partition it now, instead of partition B, partition A, and partition A according to its rows. So if I partition A according to its rows, then another way of looking at what is the matrix multiplication AB is that it is the first row of A by B, the second row of A by B, the nth row of A by B. Okay, so and we know what does this mean? Vector transpose by a matrix. It's a linear combination of the rows. Okay, so what this thing here represents is each component is a linear combination of the rows of B. And what we saw over here is that each component, so now component means column, is a linear combination of the columns of A. So what you're seeing is two different ways of interpreting what is matrix multiplication AB. The answer in the end is the same, right? Because if I give you two matrices, A and B, and I tell you multiply them together, it doesn't matter if you partition one of the row, if you partition one of the column, you can partition them however you like. The answer in the end should be the same matrix, right? It is just two different ways of interpreting the same type of operation. You could either interpret it as you break up the resulting matrix AB, you break up the resulting matrix AB as a column where each column is a linear combination of the columns of A, which was the matrix that was first, or you break up the matrix AB as rows, you partition it as rows, where each row is a linear combination of the rows of B, where B was the second guy. And the proof is the same as this proof, except that you view it as columns. Sorry, rows. Rows, instead of columns. Okay, so again, we have an example of this. So if we look at the same example, same matrices A and B as before, right? So these same matrices A and B as before. Um, but now we are partitioning A into rows. So A1, 2, this will be A1 transpose, and this one will be A2 transpose, right? So AB will be A1 transpose B, AB will be A1 transpose B, A2 transpose B, right? Right, so that's written up here. So A1 transpose, A2 transpose. So AB is A1 transpose. This here is your matrix B. This here is your matrix B. That here is your matrix B. And this is A1 transpose. This is A2 transpose. This here is B. Right? And again, when you do the matrix multiplication, notice you get the same matrix. You should get the same matrix. Okay? Now, let's put both of these things together now. So we've looked at what happens if I choose to partition a matrix as in terms of its columns. That's the first thing we looked at. We partition B in terms of its columns. Then we just looked at how to partition a matrix A in terms of its rows. Now, and we saw that matrix multiplication AB, if I partition the matrix B in terms of its columns, then it can be viewed as a linear combination of columns of A, or if I partition A in terms of its rows, then it can be viewed as a linear combination of the rows of B. But in each of these views, I only partitioned one of the matrix, either A or B. What if I choose to partition one of them in terms of rows and the other in terms of columns? Then what would matrix multiplication tell me? Again, the resulting matrix is the same, but the interpretation of what we are doing or the operation, it tells us something deep behind the idea of what matrix multiplication is trying to capture. So that's given by this result, theorem 5.6. So in this one, we are now piecing together those two things. So using the partition of A and B given in those previous results, in other words, I am partitioning A as rows. I am partitioning B as columns. Okay. Then the resulting matrix, same matrix as before. So it will be, if I want, let's look at one of them. If I want this one, the first entry, right? The first entry is given by this one. The second entry is given by this one. And that's this entry. The nth entry is given by this one, right? So that's first row. Then the second row will be A2 transpose, and it'd be this one by this one, this one by this one, this one by this one. And you get these. Okay, so this is the structure of how matrix multiplication is going to look. So now let's look at one of these entries, right? So one of these arbitrary entry over here. Let's call him AI. So it's always AI transpose B sub G. So what is this? So AI transpose is AI transpose. This was the ith row of the matrix A. B sub J, this was the jth column of B. Okay, and So what it's saying is that uh, uh let me draw this. Yeah, so it's not that's what I tried. So let me just draw it for here's A, let me use a different color. Here's B, right? So A and B may not be the same size, but of course they need to be such that the multiplication makes sense. Here is AB. Okay, so here's AB. What we are seeing there, so basically what's happening there is um, AI transpose is this row. BJ is this column, right? And the AIJ entry, so the entry on the ith row and j column. So this is the ith row. This is the j column. This is A, oh, that is AIJ. Uh, okay, let's just call it what it is, which is AI transpose BJ, right? That is the entry there. So in other words, we are seeing what the individual entry, right? What the individual entries of this product matrix AB really is. Now, when we look at dot product, so forget about this matrix stuff for 1 minute. Go back to dot product, right? Say we have some vector x, and let's just say it's x1, x2, x3, right? Let's just say we are in R cube. Now we have another vector y, y1, y2, y3, right? Then we learn what the dot product was, x dot y, right? It's the inner product or the usual inner product if we are in our Rn. And that was just the summation of x, I, y, I, right? In other words, we do x1, y1 plus x2, y2 plus x3, y3, right? Summation over I. There is another way to write this instead of using this summation formula. And you may have seen it in books already. And that is um, if we so again we're using the convention that if I write a row, then it is a transpose. If I write a column is a regular vector. So I'm going to relabel this guy to be, let's say, X transpose because it's a row, right? And and I'm going to call Y. Let me use capital Y then. I'm going to use Y to be the column. Y1, Y2, Y3, right? Let me write X again. So let me define Y to be this, and let me define X transpose to be this would be a row X1, X2, X3, right? Then what is so this is what's the size of this one? This is 3 row, 1 column. This is 1 row, 3 column. Um, so if I do X transpose Y, right? So this here is 1 by 3. This here is 3 by 1. The values here are the same. The answer is 1 by 1, which is a number, right? We know this is a number. And what would this be? So think of these as regular matrices now, right? Row matrices and column matrices. Y1, Y2, Y3, right? So these are regular matrices now. So it's this one by this one plus this one by this one plus this one by this one. Where did we see that before? Right? That is exactly this. You see, it's the same, right? In other words, what we have just showed here, well, it's not a proof. It's this I assume is the proof for R cubed, but you could generalize this to Rn. What I've just explained here is the dot product formula x dot y, which is the summation of xi, yi over I goes from 1 to n. And we could encode this formula in terms of matrix multiplication. That is X transpose Y. If you work out these two, you will get the same number, right? So you could choose to view it as a dot product of vectors, or if you want to, you could rewrite it, take one of the vector, rewrite it as a row, take the second vector, rewrite it as a column, and then do row by column multiplication, right? This is matrix multiplication. You will get the same answer. So X transpose Y, that form, something transpose something. Look where we are seeing that. That is exactly what we are seeing here. X transpose Y, right? So the individual entries, I think it's up here. Yeah. The individual entries of the product matrix can be viewed as inner products of the rows and columns, or vectors from the row space of A and the column space of B. You're taking inner products of them. And each inner product gives you an entry in the matrix AB. That is another way of interpreting what this thing is, right? And they have it over here. The scalars AI transpose BJ in their above result are often referred to as inner products, right? And now you see where they get the name from, right? So that's another way to view what those things are. Okay, so now we're going to move on to something called block partitions and direct sum. So when we have partition two matrices into blocks, we know that we could add them as long as the partitions are the blocks sizes, the size of each block correspond. So for example, if I have 2 by 2 block partitions of the matrix A and B, if the size, so they're saying each Aij and Bij is of these sizes. So this stuff here, it looks confusing, but all but all they're saying is that you could add A and B together, provided that the size of A11 is the size of B11. And A12 is the size of B12, right? Then this stuff makes sense. Okay, so you can add them blockwise. And we just saw not only could you add them blockwise, you can multiply them blockwise. But again, in order for A11 to be multiplied by B11, the sizes of these two matrices must be right? They say it must be conformal for multiplication. Right now, of course, we know by now what that means. It means when you write down the size of this block and this block, the number of columns of this one must be equal to the number of rows of this one. Okay, so we know how these block matrices multiply. And this year, we just saw a special case of that earlier. It's A1 by B1 plus A2 by B2. So let's look at some of some block matrices we'll see later down the line. If I have a matrix X and it's an M by N matrix, and I break it up into this block, M by N. And here's a mistake. Should be M by N, right? Not M plus N, M by N. Okay, so The first block here is the M by M identity. Then the N, the oh no no. Oh, sorry. This is correct. This is correct. This is correct. Right? I thought this was the matrix X. X is inserted into this block. Okay, yeah, so maybe let me draw that. Right? So this matrix here is equal to, so we have a M by M identity in the first block. Okay, so I want to draw this. What we can do, mm, let's do so. Let's do something like this. Right? So this is I am. Right? So of course the identity. So ones and then zero, zero. And this one here. Okay, so I need to um, make it square. This one here is I n. So one, 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 zero, zero. And over here we have a bunch of zeros. So this is the zero block. Okay, so this is the zero block. So all these entries are zeros. All these entries are zeros. Right? So that's the zero block. In, im, and now x. X is this matrix up here. And x is this block. And of course it's a, right? So this is x and it's we'll tool it's m rows and columns. N columns and m rows. Okay, so the size of this entire thing now, let's see if we can work out what the size of this entire block matrix is. So how large, how much columns do we have? Well, we have n columns from the x, and we have m columns. So remember the identity is square. So we have m and m, right? So it's just m by n. Sorry, m m plus n, right? Rows. And down here again is n, right? N, n, right? So how much um, so how much rows do we have? Well, we have m rows plus n. So m plus n, right? So we see that this block is actually square, right? So that's why they put m plus n. If you see m, p cross q, then these are p rows, q columns matrices. If you just see a matrix with just the index p, and it's missing the index q, then that's because it's a p by p, it's a square. So when we see m plus n, then it's a square m plus n matrix, right? And I just explained here how they got this number, m plus n, right? So that's the block. That's this block that you're seeing here, right? So that's this block matrix here. So we have that block matrix. Okay, so what are they saying? I think they're trying to invert it, right? So they want to know what's the inverse of this. So they claim that the inverse of this matrix, so it's a square matrix, so we could look for an inverse, is given by this matrix, I minus x. So we do the matrix multiplication. I by I is I plus minus x by 0, 0. Okay, so that's just I. And we do I by x is x. Minus x by I is minus x. So x minus x, that's 0. Then we do 0 by I is 0. Plus I by 0 is 0. Then we do 0 by x is 0. Plus I by I is I. Right? So this simplifies to the identity matrix, right? So now, by the way, this I and these I's are two different I's, because yeah, they represent the same identity matrix. This I here, remember from the block decomposition, it's a M by N, M by M. This I here from the block decomposition, it's a N by N. And this I here is the M plus N by M plus N identity. So even though they're using the same symbol, right? The sides are not the same. Same thing with these zeros. This 0 you see here is a M by N 0. This 0 you see here was the 0 up here, which was, what was this? M by N. Right, so just be careful with. Yeah, so what they showed is that if you have a matrix of this form, then the inverse is given by this matrix. Right, you just put minus x up here. And now, so let's say we consider this 2 by 2 block, right? So notice that this is essentially the shape of any upper triangular matrix, right? Remember upper triangular and lower triangular? A matrix is upper triangular if the leading diagonal and everything be, sorry, if everything below the leading diagonal is 0, we call this upper triangular. And we have a lower triangular, which everything above the leading diagonal is 0. Right, so this is like the triangular matrices are square matrices. Right, the only thing is this block decomposition here may not be square. Okay, so they say y is a n by n, z is a m by m. So right away, this will be, yeah, so this actually is square. Right, there will be an n plus m matrix. And they claim that this is invertible. Why? Because the inverse of it, you could easily check, is given by this matrix, right? So multiply this matrix by this matrix and see if you get the identity. Okay, so I'll leave you all to go through that multiplication. Identity 5.4 simplifies the useful fact about upper triangular matrix, which is stated in this theorem over here. Right? So in other words, what this is saying is that you can now invert any triangular matrix. Here's the inverse for it. You find the inverse of the upper block and you put it here. You find the inverse of the lower block and you put it here. And then you work out what is this product and you put it here. Right? So no need to try to invert the entire matrix. Invert the smaller blocks. Okay, so what is this theorem saying? It's saying for n bigger than or equal to 2, suppose that A are the entries of this matrix is an upper triangular matrix and has non-zero diagonal entries, right? Of course, if the upper triangular matrix has a 0 entry in its diagonal, it's not invertible, right? Because we know that the determinant, let me just say that now, the determinant of any triangular upper, lower, diagonal matrices is the product of the diagonal entries. Same thing here, right? So determinant of upper triangular, lower triangular diagonal matrices is the product of the diagonal entries. So if there is a zero on that diagonal, then the product is zero. And you know, of course, if the determinant is zero, it's not invertible. So that's why they are saying non-zero diagonal entries. Then A is invertible. Its inverse is upper triangular, right? Look, the inverse is this guy. That is upper triangular because everything below the diagonal is zero. And the diagonal entries of the inverse are the inverse of the elements, right? So this is the diagonal. This is the diagonal. They're saying the entries on this diagonal is the inverse of these entries, right? It's 1 over it. Okay. So for example, let me give you an example of that. Um, let's just say, for example, we have this matrix. 2, 1 over 7, 9, 11, right? And everything here is 0 and something up here, right? So this is a upper triangular matrix. They are saying that the inverse of this upper triangular matrix, right? Of course, it will be another upper triangular matrix, so everything below is 0. But the diagonal entries, so the determinant is the product of these numbers, like I said before. The diagonal entries in the inverse is 1 over these entries. So this is 1 over 2, which is a half. 1 over a 7 is 7. 1 over 9. 1 over 11. Okay? So the diagonal entries are the inverse of the original diagonal. Right? And these entries up here, you'll have to work out. These entries could be anything. Right? So that's what this part is saying. Okay. All right. So this next theorem, let B be a m by n, and C and X be m by n, and D be a n by n. Then this block matrix is similar to this block matrix. Again, to prove similar matrices, remember two matrices are similar if there exists some invertible matrix P such that um, M is equal to P inverse NP, right? Or if you can't remember it, this is the same thing as saying um, Q and Q inverse. Like if you can't remember, do you put the inverse matrix first or do you put the inverse matrix second? It doesn't matter because you could just relabel these matrices as Q equal P inverse. So to show two matrices are similar, we need to find this matrix, this mystery diagram P. That will turn this block matrix into this block matrix. And luckily they gave you it, so you just need to verify it. So this matrix and this matrix. So this guy here is the matrix P inverse, and this guy here is the matrix P. So you just do matrix multiplication, and you will see that this matrix turns into this matrix. Right? Well, by matrix multiplication, I mean block matrix multiplication. Okay, and now they're saying, recall that for a matrix A, if the entries are complex numbers now, the conjugate transpose, sometimes called the adjoint of the matrix, so that's denoted by A star, so we saw this previously, is the conjugate transpose. So what you do is you conjugate every entry in the matrix A and then you transpose that matrix. Or transpose the matrix A first and then conjugate each entry. So it actually doesn't matter which order you do these two operations. Conjugate transpose is two operations you need to do. Conjugate the entries and transpose the whole matrix. It doesn't matter which you do first, right? Is the matrix obtained by either first transposing A, then taking the complex conjugate of each element, or vice versa, right? So the transpose and conjugate transpose, what we call their joint, operate on block matrices as follows. In other words, we know how to conjugate transpose a matrix. But if I have a block matrix, then if I want to transpose this block matrix, then uh, so we know how to transpose a matrix. You just rewrite the rows as columns, right? This is saying you could get the transpose of this matrix by transposing individual blocks. So this block transpose, this block transpose, this block transpose, this block transpose. So you just transpose individual blocks. And instead of conjugating every entry in the matrix, you could conjugate each block, right? So um, yeah, so this is saying it holds for any m by n block. Okay, so you could transpose each block individually. Right, so you transpose each block and then you rewrite it. So so let me give you an example of this. If you have, let's say, a matrix M, and let's say it's given by this block matrix A, B, C, D. So these are block matrices. Then what this is saying is M transpose is so transpose the original matrix. So A, B, C, D. So here's A, B, C, D. So I transpose it, and then you transpose the individual block. Right? So you transpose the matrix and then you transpose the blocks in the matrix. Right? So for example, this first row becomes, you see, it becomes the first column, but it's transposed, right? And the second row, you see, it becomes the second column, but it's transposed. Each block, you need to remember to transpose it, right? And something that's going to be very useful in the last set of topics is the direct sum of matrices. Now, uh, we'll also meet the direct sum of vector spaces. The idea is the same. So a direct sum of a square matrices is a block matrix that is block diagonal and is so block diagonal means every off diagonal block is zero. Okay, so for example, so A and B are matrices, right? This symbol plus circle. When you see A plus circle B and A and B are matrices, that is telling you you are going to form this block matrix where the diagonal entries are A and B, and the off diagonal entries are all zero blocks, right? So over here we have zero blocks. Okay, so we could extend this. So if we have like all these blocks, so let me give you an example of this. So say I have Um, so our matrix A plus circle B plus circle C, right? What does this matrix look like? So this represents a block matrix where the first block is A, the second block is B, the third block is C, right? And what you need to remember here is that A, B, and C may have different sizes. So A might have size, I don't know, uh, uh, M1 by N1. B may have size M2 by N2. C may have size M3 by N3, right? And so this block here is a zero block. 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 But each of these zero blocks have different sizes, right? Um, if A, let's see if we can figure out some of these sizes. If A is M1 by N1, so A rows, so it's M1 rows, N1 columns, right? B, B is M2 rows, right? And N2 columns. And C is M3 rows and N3 columns. Right? So we could using these dimensions, we could figure out what each of these zero blocks are. So for example, this zero block I know will be M1 by N2. And I know this zero block will be N2 by the size of sorry. Let's see it's down here. Yeah. M3 rows. M2 by M3, right? So it's easy to figure out once you draw the diagram. So what I'm saying is that yes, these zero blocks, these green blocks are only filled with zeros, the number zeros, yes, but they have different sizes, right? So when we form a matrix in this way, like this block structure, by only specifying what goes in the off diagonal, and remember these are themselves matrices. A, B, and C are themselves blocks. Then we call this a direct sum of matrices. And for example, if if let's say these matrices in this example um uh, are simply scalars, lambda one, lambda two, lambda n, then what this block diagonal is going to basically come down to is like lambda one. So this is just a one by one. This is a one by one. This is a one by one. Then this is just a diagonal matrices where the entries on the diagonal are the lambdas. Okay, so that's a special case. The special case is if each of these guys are one by one. One by one means just a number. So lambda one, lambda two, lambda n. And you get this diagonal entry. And it turns out when you have matrices built in this way, using this direct sum, you could get a lot of nice properties um, for them. For example, you get this nice sort of distributive law. Then you could sort of multiply them. Then you could raise them to some power. And P here represents a polynomial. So if you plug this block diagonal matrix A direct sum with B into this polynomial, that's the same as the polynomial of A, which is a matrix, direct sum with the polynomial of B, which is a matrix. Right? So I'll leave you to sort of think about why these things are true. Right? We may use some of these results later on. And finally, uh, a very useful technique with these block matrices is that it allows us to calculate determinants, or at least break down the determinant calculation into something that might be more manageable. So we saw before that the determinant of a diagonal or a triangular matrix is the product of the main diagonal entries. And this observation could be generalized to block diagonal or block triangular matrices, right? So what they're saying now is for diagonal and triangular matrices, the determinant, you just multiply the diagonal entries. If we have a block diagonal or a block triangular matrix, you multiply the blocks there. Well, the determinant of the blocks. So for example, if A is an m by n matrix, right? And you have, so let's say for example, you want to work out the determinant of this block matrix. Then what you do is you get the determinant of this block. So this is a block diagonal by the determinant of this block. It's the determinant of In by determinant of A. And of course, we know the determinant of the identity matrix of any size is 1. So we get the determinant of A, right? And it's the same thing if you had the A up here. Now, using this lemma, we could extend this result to this theorem, where so now this is for a upper triangular, but of course you could write the same thing for a lower triangular. So let's say you have A, B, D, 0, right? So this is an upper triangular block, and this is a lower triangular block. The idea is the same, right? And what's the idea? Is that you work out the determinant of the blocks and multiply them. So over here, you will work out the determinant of the blocks and multiply them, right? And the proof here is, so for the proof, what we need to do is rewrite this block triangle in this form. So you could verify by matrix multiplication that this is true, right? That the left-hand side and the right-hand side are the same. And then you take the determinant on both sides, right? So if you call this one M, M1, M2, M3. So take determinants on both sides. Then you get the determinant of M is equal to the determinant of M1, M2, M3. But remember, you all know a rule for determinant. The determinant of AB is the determinant of A by the determinant of B. So you could also extend this result to any finite product of matrices. So this is the determinant of M1 by the determinant of M2. And these are just numbers. The determinant is just a number. Okay? And this is M1, M2, M3. And we saw from this lemma, right? Now we invoke this lemma that the determinant of matrices like this is just the determinant of the non-identity, block. So the determinant of this guy is just the determinant of D. The determinant of this guy is just the determinant of, well, it'll be I, right? It doesn't matter which of these i's you take because it will be 1. And the determinant of this block will be the determinant of A. So it's D, determinant of D by the determinant of A. Determinant of D by the determinant of A, right? So it gives you a very nice way to do these block calculations. In fact, it's not written here, but I'll write it. You might be wondering if you have a block square by square matrix, right? So this is a block matrix, and this is a square by square. Let's say it's n by n, right? Actually, let's say it's 2n by 2n. and each of these individual block is n by n, right? That makes it easier. Then the determinant of A, B, C, D is exactly what you think it will be. It will be the determinant of A by the determinant of D. Remember how if you have a matrix A, B, C, D, what is the determinant of this guy? It's AD minus BC. Same thing here. But again, you need to remember these A's and B's and stuff may not be numbers. These are blocks, block matrices. So it's the determinant of A by the determinant of D minus the determinant of B by the determinant of C. So we can actually generalize this theorem into, more general statement. And the hope is in all of this that these determinants are easier to calculate than the determinant of the big matrix. Okay, so that's it for this video. So hopefully that this helps explain the idea and the use of this block matrices.